Thank you so much for the introduction. It's my great pleasure to be here at the Open Data Science Conference today. And so I'll be sharing with you some of the recent exciting work around building reliable open world machine learning models that can detect out of distribution data. And feel free to ask any question during the talk. And if you do, please go ahead and post in the channel, the QA channel, and I will be addressing all the questions towards the end of the talk. Now let's get started. So I would like to open up the talk using the following example. Imagine yourself trying to develop an app that can automatically classify and recognize the pictures of food taken. And so it can show users some nutrition information and possible recipes that can be made with it. And so when users go to grocery store, they can just snap a photo and get some inspiration for what to cook for dinner. And to do so, the typical standard workflow is to collect the training data and then train on your favorite neural network and then deploy this model. Now, after going through all this workload, well, you think you're done with all the work, more unexpected work has just begun. And why do I say that? Because the classic machine learning assumption is that the training and test data distributions match each other. And so you would hope the users would only upload photos of food which just look like your training data. And this is what we call a closed world setting. And the reality is more closer to an open world setting where the training and test data distributions can be wildly different. And for example, the test data can be anything beyond what you would expect in such an open world. And this is one of the most I would say important realizations from my previous work experience in industry. And so this brings us to the fundamental question, which has been governing my research. How can we build machine learning models that function reliably in such an open world? And an important step towards this goal is to be able to detect and identify out of distribution inputs. For example, when this bird image is fed into the food image classifier that you just trained on, ideally this model should identify this picture to be somewhat unusual or out of distribution instead of characterizing it into one of the known classes, because this bird has nothing to do with the food categories. And this problem is even more concerning for those safety critical applications such as identify unseen unusual disease, such as COVID from regular pneumonia based off on chest X-ray scans, or in autonomous driving, identify unexpected objects that were previously unseen. And this way the model can take enough precaution and early prevention. And so today I'll walk you through some of the exciting work that my lab has been working on in designing algorithm, theory, and practice to advance the state of art in for this problem of out of distribution detection. And before we jump into the specific works, let me just spend maybe 2 minutes to explain to you why this problem is hard. Why do we even bother solving this problem? And to simplify things a bit, I will use this traffic sign classification as a run example. And so if we take any off-the-shelf architecture or network and train the model on this traffic sign dataset, and typically we use softmax to measure the probability for the image to be associated with each class. And this is a vector that sums up to 1. And the softmax confidence is defined to be the largest probability across all the classes. And so when the model converges, it will produce a very high confidence for those traffic sign images. And this is something not surprising because networks is trained with a cross entropy loss, which intends to amplify that. So now let's zoom into this cross entropy loss. And imagine this input just go through some convolutional layers and produce a softmax prediction on the left side. And it assigns a probability 0.8 for one class and 0.2 for another. And on the right side is the true ground truth label, which is one hot embedded. And so in this case, the cross entropy loss is the negative of log 0.8, which is the probability that corresponds to the ground truth. As you can see, in order to minimize this cross entropy loss, this network would push the predicted probability to be as close to 1 as possible, right? In other words, it's pushing the confidence to be very high. And so this explains why the network is producing high confidence for the traffic sign data. However, it can become a problem during test time if we're taking a completely irrelevant picture, such as a mailbox, and feed into this network. And ideally, we would hope the network produce some low confidence score in predicting this to be a traffic sign, because it has nothing to do with traffic sign, right? And we call this image out of distribution example because it's sampled from a data distribution that is not what the network was trained on. And it turns out neural networks can be quite overconfident to out of distribution examples or OOD examples. And this is what researchers observed in a series of experiments on modern neural network architecture. And so to see this, we can sample a bunch of in-distribution images and then calculate their confidence score indicated below. And we can do so similarly for a bunch of OOD images and calculate the confidence. And so if we take a large collection enough of samples and plot the distribution of confidence score, this green curve shows that for in-distribution images, and the gray curve is for OOD images. And as you can see, these two curves tend to overlap a lot. What does that mean? Essentially, you can't just simply draw a threshold based on the confidence to tell them apart. And so the question now here is, how can we then, reliably distinguish these two types of data? How can we fix this problem? And we proposed this work Odin back in 2018, and nowadays it has become one of the most popular and commonly used methods for OOD detection. And so Odin is composed of two components. The first technique that we introduce is called temperature scaling. And here's how temperature scaling works. So recall this is how we previously calculate softmax. Now, instead, we divide this original output, f of ix, in other words, the logit output, by a constant factor, which is called temperature T. And then we, after this scaling, we calculate the softmax the usual way. And so you might be wondering why temperature scaling is useful for OOD detection. First, because it has a strong smoothing effect, which would push all the softmax score closer to 1 over n. And here n is the total number of classes. So if you have a 10-way classification, all the score would be closer to 0.1. And more importantly, it will make the softmax score distribution more separable between the two. And so this green and gray curve becomes much more separable compared to what we saw earlier. And we can actually explain this mathematically. So to see this, we can approximate this confidence score using this Taylor expansion around x and t. And so when this temperature is sufficiently large, it's safe to ignore this higher order term. And so we can just focus on this first order term here. What this first order measures is the extent to which the largest unnormalized output, or the logit, deviates from the remaining outputs. And so if we take this first order measurement and empirically measure how this distribute for in distribution, which is in red curve here, CIFAR 10, that's our what the model is trained on, and all the other curves are OOD data sets that we evaluate against. And so you see here, there's a clear separation between the red and all the other curves. And so this explains why temperature scaling helps the OOD detection. And we also have, more detailed analysis on this higher order term, but I won't go into the detail here for the time being. And so hopefully explains the temperature scaling part. And in addition to this, we also make some minor changes to the input space, which would help further improve the detection ability. And so we take this original input and pass through this network, and then we calculate the gradient of the loss with respect to the original input. And so now we subtract this, the gradient we just calculated with magnitude epsilon, and get this slightly perturbed image. And so if you're familiar with atmospheric examples, this is a very, very similar, but in the opposite direction, the way that we're adding the noise. And so by subtracting the noise, we would essentially push the confidence to be even higher than where it was before. And I won't go into details, but mathematically we can show that by adding this noise perturbation. The interesting thing here is the increment for the in distribution examples. So the gap between the two green curves are much more significant than the gap between the two gray curves. And so the result of that is to make the two curves more separable. And in other words, that can lead to stronger OOD detection performance. And so now with these two techniques, temperature scaling and input perturbation, we're able to make a good use of this in practice. So now during test time, we first built this detector, which is which based on a threshold comparison. And so the threshold delta is chosen so that a high fraction of in distribution images, let's say 95%, is correctly classified. And this has two advantages. First, our method does not require any retraining of the neural networks. So it's really conveniently plug into any pre-trained model. And second, it preserves the classification accuracy, right, because we're not changing the parameterization of the network. And so in practice, what you can do is to take this OOD detector, G of X, as an extra safety layer for your network during inference time. So when an input image comes in, we first perform the detection of in distribution versus OOD. If it's in distribution, and then we pass this to the downstream classifier. And otherwise, we would flag this image for further inspection. And so to verify the effectiveness, we train our model on state-of-the-art architecture back then, DenseNet on Cypher 10. It's a data set composed of 10 different classes of animals and airplanes and so on. And so this is the network that was trained on. And then we take a subset of ImageNet to evaluate on the model we just trained, right? So this was exactly the same model trained on Cypher 10. And here is the evaluation results. On the x-axis, I'm showing you the false positive rate, which is the fraction of out of distribution images that are misclassified as in distribution. And on the y-axis is the true positive rate, which is the fraction of in distribution images correctly classified. So as you can see, when the true positive rate, TPR, is 95%, here this green horizontal line, right? Our method, indicated in blue, is able to reduce the false positive rate from 34.7 down to 4.3. And this is a very significant improvement in terms of false positive rate. And so we test thoroughly on more data sets and consistently observed quite significant improvement. So the green bar is indicating Odin, our method, and the blue bars are the previous method using maximum softmax probability. And so I want to mention that there has been a lot of really interesting follow-up works in this area. So a lot of progress has been made over time. And here I'm highlighting in green a few works that our lab has been kind of contributed in recent years. And among those, I'm particularly excited about this new work on energy-based out-of-distribution detection, which was accepted to NeurIPS last year. And in fact, when we released the paper last year in October, the Twitter bot told me that this was the most popular computer science paper that was tweeted during the day, which was really encouraging to see. And so energy-based model has been around for a while. To give you some background, an energy function would take an input x and corresponding label cat y. And it goes through this energy function and it would produce some scalar, which we call energy. And this energy is lower for observed data points and higher for unobserved data points. And so this function can be non-probabilistic because it's a free-range scalar. And you can turn this into a probability through Gibbs distribution. And so this is exactly the same equation that I just showed. Essentially, you can calculate probability of a given label conditioned on the input in terms of exponential of the negative energy, and then divided by some partition function. And this partition function is aggregating all the y label space. And so if you equalize the equations on both sides, we can express the free energy as the negative of the log partition function. Right, so all this is the previous contribution. And so you might be wondering how energy-based model is related to neural networks. Well, it turns out a neural classifier can be interpreted from an energy-based perspective. So now let's consider a neural network that is producing output logit, F1, F2, and so on. And then you pass this through a softmax activation function, which would produce normalized probabilities P of y conditioned on x. And so this is exactly the equation of softmax, which you have seen this quite a lot during the talk. And now if we define this energy function, E of x comma y, to be the negative of the logit for each class, effectively this turns into something that we just saw right earlier. And so now the free energy, recall this is how the free energy was previously defined in a continuous space y. Now we can replace this integral with summations across k discrete labels. And so for every input and a given pre-trained neural network parameterized by f, this is how energy function is defined. And in practice, this can be very conveniently implemented through a log sum exponential operation. And so in this work, our key idea really is to replace softmax confidence score with energy for OOD detection. And using softmax score, we've already seen this would incur very high confident predictions for OOD images. And using energy score in contrast, the distributions now become much more reasonable, right? In particular, the in distribution no longer have this spiky distribution. And it turns out this is the really, I would say, appealing property of energy score. And here is some theoretical explanation. I will try to keep this part short, but the key idea here is that energy score is aligned with the underlying probability density of the in-distribution data P of x. And so in other words, if a data point has a higher log likelihood, and it would have correspondingly lower energy, and vice versa, right? And this density can be very useful indicator for measuring or performing inference to tell apart in-distribution versus OD. And because energy is aligned with this log of likelihood, that's why you can use this as a more reliable measurement for OD detection purposes. And we also showed some interesting analysis here why softmax confidence, on the other hand, is not useful for OD detection purpose. Because mathematically, we can show that it's not aligned with the log likelihood, right? So in other words, a data point with low likelihood does not necessarily mean it has a low softmax confidence. And so to evaluate and compare our approach, we train a model again on CIFAR 10. This is the same data set that you have just saw earlier. This is the in distribution. And we evaluate on SVHN as the out of distribution data. And so here is the evaluation results. On the left side, we show that for the traditional softmax approach. And on the right side is using energy score. And interestingly, you see this purple curve for in distribution becomes much, much smoother. And in fact, so is out of distribution curve here. And the false positive rate is reduced from 48.87 to 35.68. So that's quite significant reduction. And this is both based on when the true positive rate is 95%. So in other words, your detector can make much lower error under the same true positive rate. And so we tested more thoroughly on a few more data sets. And here in this case, 6 different out of distribution data sets. And we consistently observe a significant improvement here. And again, the blue bars shows that for softmax, and the green bars are energy. And what I would also like to mention is energy is practically very easy to use because it doesn't require any hyperparameter tuning. For example, in case you're wondering how this compares to the method Odin that I just described. And so both methods are working quite competitively, but Odin would require this hyperparameter, which is the noise magnitude that needs to be tuned, whereas energy is completely hyperparameter free, right? So it's much easier to use. And so this is certainly nice, but we can, even do better. We thought, what if we were allowed to retrain or fine-tune this network and maybe shape the energy surface explicitly and make this energy gap even bigger between in distribution versus OD. And so we can achieve this by using the following training objective, which is a combination of standard cross-entropy loss, which is used for classification. And on the right side is our proposed energy regularization term. And intuitively, what this energy regularization is trying to achieve is to push all the energy to be lower than certain margin parameter Mn for the in-distribution data. And in contrast, we're trying to push the energy to be higher than certain margin M out for OD data. And so this would naturally create a strong gap in between these two. And so here is the evaluation results. On the right side, I'm showing you the results of performing fine-tuning with this new objective. And you can see that the two distributions become much more separated, right? So this is the result of explicitly regularizing the energy. And now the false positive rate can be reduced even further, down to 1.18. And notice that all these three plots are based on the same in distribution data sets, which is CIFAR 10, and evaluated on the same out of distribution data set, which is SVHN. And again, we tested more broadly on a suite of 6 different data sets. And here the yellow bars are indicating the results of training with energy fine tuning. And so you see there is significant gap between the blue bars and the green bars, which is based on the pre-trained model without any regularization added, without retraining. And the yellow bars are obtained by adding this energy regularization term. So it will require some retraining, but the result of that is much stronger OD detection performance. And so we actually compared our approach with a collection of competitive methods in literature. And here is we're showing the false positive rate, for example, and ARC. So lower is better for the first column, false positive rate, and ARC is higher, the better. And you can see our methods works competitively and establish the state-of-the-art performance on this challenging task. And I would also like to mention that we're able to achieve this performance without compromising too much on the in-distribution classification. And so you see on the rightmost column is the original classification test error on CIFAR 10 versus CIFAR 100, right? So in other words, you know, our method can give you stronger safety guarantee by ruling out a lot of potential OOD, and at the same time, you can still do pretty well on the original image classification task. And so that's what I mean by overall a much better trade-off here. And in case you're interested, our work is open source, and the code code and demo is available on GitHub. And here's the link in case you're interested in trying out. And so next, I would like to switch gear a little bit and briefly just talk about a recent project that my students worked on in last fall semester and was recently accepted to CVPR this year. So the project is called multi-level out of distribution detection, which in short as MOOD. And so MOOD sets out to achieve this task of performing efficient out of distribution detection. And if you think about some of the previous work that I described, and including many other works in the field, mostly rely on outputs derived from the final layer of this neural network, right? So for every image, we basically have to take this entire feed-forward path, go through all these convolutional layers, and get to this final stage. And as you can imagine, it quickly becomes computationally very expensive if we're dealing with very large deep neural networks. Or for example, some of the bit models released by Google recently can have up to hundreds of millions of parameters at its largest capacity. And this can be undesirable for some of the safety critical applications such as self-driving cars, where higher computation cost directly translate into higher latency for the model to take prevention, right? So in those applications when real time matters, you want to be able to detect as early as possible. And that's exactly the motivation for this work. And we thought, is there any way we can perform the detection much earlier in this network without really propagating through all those layers? And it turns out it's very feasible. And so, for example, if we take a model that is trained on all the colorful images of, animals, and you can imagine, in order to detect this black and white images as OOD, the model can just rely on some of the low-level features instead of, propagating all the way to the end. And so the idea is to take early exit for those easy OOD examples, as I'm showing you here, exit of 1. And for some of the more complex inputs, the model would then propagate through some of the upper level. And the level that's taken by this model would be determined based on the measurement, which we call complexity. So I won't go into the details here, but a key technique that we propose in this work is to rely on this complexity-driven measurement for automatically determining which exit the model should be taken. And if we rely on this dynamic exiting strategy, our method is able to achieve or save up to 71.05 computation measured by flops, and also with improved OOD detection accuracy. So again, this is quite encouraging results because we're able to save computation and at the same time do better in OOD detection. And this is the last piece of work that I would like to just briefly mention because I know we're running out of time, and I also want to save some time for QA. So let me maybe just briefly mention the motivation and why this problem is interesting and worth working on. And so this is the robustness aspect of out of distribution detection. And if you think about all this previous work that we have done, right, we often care a lot about accuracy. How can we reduce the false positive rate in terms of OOD detection? But it's really unclear how robust these OOD detection methods are, right? And so, for example, imagine we have two types of data where this black curve is the decision boundary between OOD and in distribution. And you can imagine maybe with some small perturbation in this input pixel space to this OOD data, and that can maybe lead to a change of the decision boundary, right, for the point to go across to the other side. And so we ask this question of how robust are these OOD detection methods, and if not, how can we robustify these detectors? And to give you even more straightforward picture, these are some of the failure modes that OOD detection methods can encounter. The first leftmost one is the standard case when there's no perturbation added, all the images are just natural, unperturbed. And the middle one is when adversarial perturbation is added to this input image, and so it can fool this detector to be misclassified as in distribution. And if it's misdetected, it would then trigger this downstream prediction for the CNN, and a meaningless label such as stop sign would be predicted. And you can imagine this misprediction would trigger some action from the car, right, which is undesirable. And so that's why this problem is quite important. And on the right side is another type of small perturbation, such as due to lighting changes or some natural corruptions due to weathering, motion blurring, and so on, right? So all this physically plausible corruptions might also cause this decision to be changed for OOD detection. And so this is the illustration of when the green dots cross the decision boundary to be on the other side. And our key idea here is to propose this message called ATOM, stands for adversarial training with outlier mining. And this is the state-of-the-art method in terms of robustifying OD detection. And our key idea is very straightforward. On the left side is the case when we have a mixture of Gaussian. Think about the N distribution has 3 classes, C1, C2, and 3. And the green dots are the auxiliary outlier data that we can rely on to approximate this decision boundary between the N distribution and OD. And when you have the key here is if you don't select those informative data points, you would end up getting a very loose decision boundary, right? There's some large space in between the outliers in distribution. And that's what makes the OD detector very vulnerable to this small perturbations. And our key idea is to be very intentional, deliberate about choosing the outlier data sets that is mostly closer, sitting on the decision boundary of the closer to this black dashed line. And so you can have a tighter estimation on this decision boundary, which results in a more robust classifier. So that's really the idea of performing what we call informative outlier mining. Of course, I won't go into the details here. If you're interested, we have also open sourced our library implementation, and also papers also available on our archive and also my website if you're interested. And so here's the quick review of the performance evaluation. And so we're reporting false positive rate for on the x-axis are all the state-of-the-art approach, and the green bar is the performance under attack. And so you can see without attack, a lot of these methods are doing quite well, right? The false positive rate, for example, of outlier exposure is reaching 0.66, which is encouraging. However, all these methods are pretty vulnerable when we're adding this adversarial perturbations. And ATOM, which is given on the rightmost column, sets the state-of-the-art results on both clean and perturbed OD data. And so you can see the blue bar, which indicates the results of natural unattacked, unmodified images. It's able to do fairly well. And in addition to that, it's able to produce low false positive rate for the adversarially perturbed images as well. And so overall, it achieves a much better trade-off. And we in fact also evaluated on more types of corruption that are more physically plausible. That is, less artificially constructed, such as adversarial images. And so, for example, when we're adding this lighting change, contrast, and motion blurring, and so on, our method is able to actually generalize to those naturally occurring perturbations, which is very encouraging. All right, so I would like to spend the last maybe 1 minute or two just to recap today's talk. I know it's a lot to digest, so I hope this summary can be somewhat helpful. And then afterwards, I'll be taking the questions from the chat thread. And so I first talk about a few methods on out of distribution detection or uncertainty estimation. And I've shown you that softmax scores can suffer from this overconfidence issue, and therefore it is not optimal for OD detection. And in fact, we have also provided some mathematical explanation to back this up. And our method, Odin, which was published in 2018, helped calibrate the softmax confidence, which improves the OD detection significantly. And energy score is our latest development, which we built on top of the previous work. and it's a theoretically more principled way of measuring OOD uncertainty. And compared to previous approach, it's also much easier to use because it's hyperparameter free, and you can plug into any pre-trained model and get a good performance. And if you have access to some auxiliary outlier data, you can in fact perform regularization to even boost the performance through the energy regularized learning. And in the second part of the talk, I also briefly, very briefly touched upon the computation efficiency aspect of OOD detection. And I didn't include this in the slides, but that was the work on multi-level OOD detection, which is the one of the recent work at CVPR, where the goal was trying to achieve good computation, low computation cost, while being able to perform detection accurately. And the last aspect is the robustness of the problem, where we show almost all of those state-of-the-art methods, despite their high accuracy, are unfortunately pretty fragile under adversarial and physically plausible corruptions. And this can cause some really safety concerns when these methods are deployed. And so that's why we need a robust OOD detection mechanism. And our proposal, Adam, on adversarial training with outlier mining, can substantially improve these worst case performance. And it also sets promising performance on the clean data sets as well. So overall, it has pretty good trade-off performance. And I think that's all I have for today. And now I would like to let me exit, and I'd be happy to take questions if there is any from the chat thread. So I'll stop showing screen. Oh, actually, I can just leave this on. And I'll click on this chat thread. I don't see any question here. And if you have any question, feel free to type in the chat thread. I'd be happy to address those. And I would like to thank all of those who are here for the talk today. Thank you so much.